Good morning. Hi, I'm working on section 7.2 today, trying to do a quick lesson on what we worked on Friday. So we're looking at volume by cross-sectional areas, and I'm trying this from home, so I've got to work with the bamboo pad. The sketching may be a little bit different. What we're going to do is take, in this case, it looks like squares, and set a bunch of squares on end, and they'd be rectangular prisms, and fill the space with squares. So what we have to do is figure out the area of the square and multiply it by the width dx, filling this entire region. So that's the general idea. Let me show you in Sketchpad what this looks like. Here, if I have a circular base and I drop that to a flat axis so we can kind of see it, we're going to prop 4 squares upright in it. So what we're going to do is basically cover this region with squares that get larger and larger as I move towards the diameter of the circle. And then they'll start getting smaller again. If you want to see, here's, a square that's continually moving across the circle, getting larger. Now it's starting to get smaller and smaller until it gets down to nothing. I'll show you what the solid created looks like by sweeping the square. And what we're going to try and do is get the volume on this solid once it's built. So there's what the solid looks like. And we can use integration to calculate the volume for us. So here you can kind of see that square row moving through the circle. So what I have to be able to do is calculate the area of the square. So back to our problem. If the cross sections generated are perpendicular to the x-axis, then their areas will be functions of x, denoted by a of x. The volume of the solid on the interval from a to b will be volume from a to b of a of x dx. So a fairly simple formula, and this will be our volume. This right here represents area of that cross-sectional piece, and then here is the thickness. So if I take area times thickness, we get volume. That's the main idea. So what does it look like in an example? Find the volume of the solid whose base is the region inside the circle, and make this 25 so that we get a matchup with the equation I wrote right down here. So if y squared plus x squared equals 25, we're going to take cross sections perpendicular to the x-axis that are, in this first case, let's do squares. So we're going to lay in, just like you were seeing on that dynamic software that we were just looking at, we're going to lay in a bunch of squares perpendicular to the x-axis all along the region bounded by the circle. So my main task is to get a of x here. What is the area of the square, which would be changing as it moves through the circle. So here's our square, and the area, then I need to find the length of it. Well, the length of it's going to correlate to the length of a chord in the circle. And we have this equation, so let's solve for y. I'm going to start with y squared equals then 25 minus x squared. And square root both sides, and we get y is equal to plus or minus the square root of 25 minus x squared. Hard to write on this bamboo. And this is plus or minus, not 4. So now I know that this top circle is represented by the square root, the positive square root, so 25 minus x squared on top. The bottom circle is represented by the negative square root of 25 minus x squared. If I add these two curves, or get the distance between the two curves, I could take this top curve minus the bottom curve and get the length of the chord. So what it turns out then, the length is actually equal to 2 of the square root 25 minus x squared. And you get that by taking, the positive minus the negative here. And minus a negative makes it plus, so I get square root 25 minus x squared plus 25 minus x squared, giving us 2 of those. That would be the distance of our square. Likewise, then the height of the square is the same. So to calculate the area of a square, or a of x in this case, all I need to do is take 2 square root 25 minus x squared and square that, which would turn out to be 4 times square root's going to go away once we square it, 25 minus x squared. Distribute through, and we're looking at 100 minus 4x squared. Excellent. This is what we were after. Once we get the area of our perpendicular section, we're in good shape, because now all we have to do is integrate over the region of the x-axis, and in this case we're going from -5 to +5. So sweeping the whole circle along the x-axis, -5 to +5, of a of x would be 100 minus 4x squared multiplied by the thickness dx. And if you integrate that, you will get the answer, and I believe on this one it was 666.667 units cubed.